carry on with the second part of the lesson, conductors and insulators. When the balloon and your hair are charged by rubbing, only the rubbed area becomes charged and there is no tendency for the charge to move into other regions of the material. In contrast, materials such as copper, aluminum and silver are charged in some smaller regions. The charge readily distributes itself over the entire surface of the material. Why does this happen? To understand this, we first need to understand what conductors and insulators mean. What is meant by the term electrical conductor? Provide a few examples. I'm sure that all of you know what electrical conductor means, and you can also give examples. However, conductors allow electrons to flow freely through them, such as silver, copper, aluminum, and other metals. What is meant by the term electrical insulator? Provide a few examples. Electrons do not flow freely through insulators. Insulators can be plastic, rubber, glass, wood, paper. So why do conductors and insulators behave differently? Outer electrons in metals are loosely bound to the nucleus and relatively free to move. Charging by contact. There are two kinds of charging which we are going to speak now, charging by contact and charging by induction. Let's start with charging by contact. Both insulators and conductors can be charged by contact. Rubbing two materials together results in a transfer of electrons. When charging metal, the charge may move through your body into the ground. The metal and your body are conductors, so the charge moves through them. You must hold the conductor with an insulating material such as rubber gloves to keep the charge on the metal. Charging by induction. A charged rod, this blue rod here, is held near a metal sphere. Why do the charges in the metal arrange themselves as shown in this figure? The repulsive force between the electrons in the rod and those in the sphere causes a redistribution of negative charge on the sphere, as shown in the figure. As a result, the region of the sphere nearest to the negatively charged rod has an excess of positive charge. Now, if this metal sphere is connected to the ground with a conductor, you see this black conductor here, why did some of the electrons move off the sphere? The sphere is considered to be grounded. When a grounded conducting wire is connected to the sphere, some of the electrons leave the sphere and travel to Earth, which can be considered an infinite reservoir for electrons because it can accept an unlimited number of electrons. So all the electrons are going to Earth. The conductor connecting the sphere to ground is now removed, so we don't have the conductor to the ground anymore. What type of net charge does the sphere now possess? If then the wire to ground is removed, the conducting sphere is left with an excess of induced positive charges in the part nearest to the rod. And then when finally the negatively charged rod is removed, why do the charges move into the positions shown, as it's shown here in the figure? When finally the negatively charged rod is removed, net positive charge remains on the ungrounded sphere. The motion of negative charges on the sphere